Okay. Okay, good morning. Can you hear me in the back? Oh. Can you hear me now? Yeah, okay, thank you. Okay, today we are starting the part on lossy compression. First, we are going to see algorithms for quantization. And then we are going to give these algorithms an information theoretical interpretation by using the so-called rate distortion function. We're not going to see specific algorithms for lossy compression targeted to speech compression or video compression, because there is not sufficient space in the course for that. So we are only going to focus on algorithms for quantization. Oh, so what's going on here? The screen sharing is paused. Why is it paused? I don't know. Stop share and share again. Okay. Okay. You all know that real numbers are approximated by a decimal expansion that requires a number of digits, and therefore the better is this approximation, and the closer we can represent a real number. Actually, when we write a real number, we usually mean that the real number is inside a certain interval. So that, for example, if we write 3.14 and we say that the real number A is equal to 3.14, that means that this real number is inside an interval that goes from 3.135 and 3 0.145. And the real number is somewhere inside this interval, but we do not know exactly where it is. Improving this approximation means that we decrease the size of the interval. And to do this, we actually require to have a very large number of digits. So instead of using, for example, just 2 digits, like in this case, we can use 3 digits, 4 digits, and so on. And by increasing the number of digits, we improve the approximation, and we decrease the size of the uncertainty interval where the real number is located in. So precision is related to the number of digits that we use for the representation of a real number. We can represent real numbers in decimal form, but we can also represent them in a binary form. And it is exactly the same thing. The more binary digits we use, and the smaller is the uncertainty interval where the real number is contained. If we want to describe completely and exactly a real number, the only way is to use an infinite number of digits, but we know that this is not possible because we are unable to represent a real number by an infinite number of digits. Of course, there are exceptions to this rule because, for example, we can represent exactly integer numbers. We can also represent exactly rational numbers. And in general, we are able to represent exactly algebraic numbers. We also have the possibility of represent certain non-algebraic numbers like Greek pi through some properties of them, through some algebraic definition, but this is not the digit representation, the numerical representation. The numerical representation, for example, of Greek pi requires an infinite number of digits. And this is a common characteristic of all real numbers, that if we want to represent them precisely, we need an infinite amount of digits. Now, if we instead use a finite amount of digits, we are going to have an uncertainty in the position of the real number over the real line. This uncertainty can be represented by an interval, and we can say that we know that the real number is inside a certain interval, or it can be also represented by using a concept that is the distortion. In particular, this is useful, the distortion, to represent the representation error for a real number that is actually a random variable. So we don't know exactly where is the real number, and we say that there is a distortion in the representation of the real number. And there is a relationship between the number of bits that we are using to represent a real number that is also a random variable, and the distortion of this real number. And this relationship is studied by the rate distortion theory. The rate distortion theory essentially finds the functional dependence of the rate in terms of number of bits per symbol that are used where symbol is the random variable essentially, and the distortion that we have. That is, the more the more bits per symbol we use, the lower is the distortion. When we use an infinite amount of symbols, we expect that the distortion goes to 0. Before looking into this probabilistic theory, we consider the problem of quantization in terms of representation of a random variable through a finite number of bits. And we start with a simple example. Let's consider a Gaussian random variable with 0 mean and variance 1. You know that the Gaussian random variable with 0 mean and variance 1 has a distribution that more or less looks like this. It has a maximum in correspondence of 0, and it looks like a bell, and for this reason it's called a bell-shaped curve. And this probability density function can also be expressed analytically by the exponential of minus x squared over 2 divided by the square root of 2 pi. This is x, the real number axis, and this is the probability density function of a Gaussian random variable with 0 mean and variance 1. Now let's say that we want to represent this Gaussian random variable by using only 1 bit. What can we do to obtain this? Well, we can say essentially that the random variable can be positive or negative, because 1 bit essentially allows us to say if it's positive or negative. And we want to do something more. We want to replace the random variable with a number, and at the same time, this number should be as close as possible to every value of the random variable. So we choose a certain number that we call a, and we say that our random variable is replaced by minus a if it is negative, and by plus a if it is positive. We want to do this in the most accurate way. And to measure the accuracy of this representation that we call quantization, we use the mean square error distortion function. That is the expectation of x minus x hat squared, where x hat is equal to plus a if x is greater or equal to 0, then 0, or minus a if x is negative. Now, among the infinite possible choices for a, there is one that minimizes the distortion, that corresponds to a equal to the square root of 2 over pi. That's approximately 0.8. And by using this value of a, we obtain the minimum distortion that is equal to 1 minus 2 over pi. That's equal to 0.36. So if we use 1 bit for the representation of a Gaussian random variable, we can achieve a distortion that's 0.36. Now let's see how we get these numbers, and later we are going to see what happens if we increase the number of bits. The calculations are rather simple. we need to calculate the distortion. And so we divide the real line in two parts, the parts of negative numbers and the part of positive numbers. And we integrate x minus x hat squared over these two intervals. When x is negative, x hat is minus a, so x minus x hat is x plus a. When x is positive, x hat is plus a, so x minus x hat is x minus a. And in both cases, we add the square because the distortion is defined as the average of the mean square error of the square difference between the random variable and its quantized value. In both cases, we multiply by g of x before integrating, because g of x is the probability density function of our Gaussian random variable. Now, we can calculate this number, of course, but we want to, first of all, find what are the values that what is the value of a that minimizes the distortion. And we can do this by taking the derivative of d, which is a function of a, with respect to a itself. We obtain that this derivative is 2 times the integral from minus infinity to 0 of x plus a g of x minus 2 times the integral from 0 to infinity of x minus a g of x. And if we expand these two integral, we obtain that this is equal to 2a minus 2 times the integral from minus infinity to infinity of the absolute value of x, g of x dx, which is this term here is the expectation of the absolute value of x. 2a comes from the fact that if we extract from the integrals the constant a, we have 2a that multiplies the integral from minus infinity to 0 of g of x plus the integral from 0 to infinity of g of x, which is obviously equal to 1. And so this justifies the presence of this 2a. If we set the derivative equal to 0, then if we set this is equal to 0, of course, we can get that a is the integral from minus infinity to infinity of the absolute value of x times g of x, which is the expectation of x in absolute value. We can calculate this by taking the integral from 0 to infinity and multiplying it by 2, because g of x is an even function. And so we have 2 over the square root of 2 pi times the integral from 0 to infinity of x e to the minus x squared over 2 dx. Changing the integration variable from x to u, where u is x squared over 2, and therefore the differential of u is x times the differential of x, we obtain 2 over the square root of 2 pi times the integral from 0 to infinity of e to the minus u. And this integral, since the primitive function corresponding to e to the minus u is minus e to the minus u, this integral is clearly equal to 1. So we get the factor here as the final result that can be simplified to the square root of 2 over pi. That's 0.79. Now we can use this value of A in the expression of the distortion. We can obtain that this is equal to 1 plus A squared minus 2 times A times the expectation of the absolute value of X. And if we complete the calculation, we obtain that this is equal to 1 minus 2 over pi. That is 0.36. At this point, we want to see if by increasing the number of bits of quantization bits, that is what we call the rate, and if we increase the rate to 2 bits, we want to see what happens to the distortion. Well, we can see that analytically, the problem becomes more difficult. However, we can find an algorithm that allows us to calculate the optimum quantization points, like in the previous case, the points minus A and plus A. Given the number of quantization points that we are looking for, which is related to R, because if 2 to the R is the number of quantization points. So in the previous case, R was equal to 1, and we had 2 quantization points. If R is equal to 2, we're going to have 4 quantization points. And because of symmetry, we have 2 variables to consider. Instead of only A, we could write that we have to find A and B. But nevertheless, the problem is analytically a little bit more difficult than before. So there is this general algorithm that minimizes the average distortion. And this algorithm is called the Lloyd algorithm, or sometimes the Lloyd-Max algorithm. This Lloyd-Max algorithm is used for one-dimensional quantization, and it's very stable and very effective. It is an iterative algorithm, so we have to repeat a number of calculations several times, and it starts from an initial quantization, an initial set of quantization points that sometimes are chosen randomly. We just pick up them randomly, and this initial quantization, this initial set of quantization points is progressively improved. That is, the corresponding distortion is progressively improved by this alternative algorithm until the minimum distortion is found. So the next thing that we want to see is how this Lloyd algorithm works. And this is the general setting that works for every probability density function. We pick up a random variable x, and we say that we want to quantize it by using n quantization points. N quantization points corresponds to R equal to the logarithm in base 2 of n bits per symbol. So the coding rate of this quantization is the logarithm in base 2 of n. We can also define a number of thresholds that divide the real line into n intervals, and these thresholds are t1, t2 up to tn minus 1, so that the real line, for example, if n is equal to 4, the real line is divided in 4 intervals, and the thresholds are these points t1, t2, and t3. The quantization points are located somewhere inside these intervals, and this is x1, this is x2, this is x3, and this is x4. We also can define the limiting thresholds, t0 as minus infinity, and t4 as plus infinity. This, of course, is in the case that n is equal to 4, and we have 4 quantization points, but it works with any number of quantization points, that is with arbitrary n. Once we have provided these definitions, we can calculate the distortion function. Distortion function that depends on the thresholds and on the quantization points. That's because when the random variable belongs to one of these intervals, we represent the random variable by the corresponding quantization points. So if x is between t1 and t2, we represent x by x2. In this way, the distortion is a function that depends on the vector of thresholds t and on the vector of quantization points x, and it's the sum of n integrals. We write it as the sum of n integrals because we need to specify which quantization point we are going to use. And so when, for example, in the case n equal to 4, we are in the first interval that goes from minus infinity to t1, the quantization point is x1, and therefore we are going to integrate, in that case, x minus x1 squared times the probability density function from minus infinity to t1. When x is between t1 and t2, we are going to integrate x minus x2 squared times the probability density function, and so on. And in this way, we have the sum of n integrals from t sub I minus 1 to t sub I, that are the two thresholds delimiting the quantization interval. And we integrate the x minus xi squared times the probability density function. Of course, these integrals are integrals of a non-negative function. In general, this is a positive function, at least somewhere. And therefore, the distortion is always greater than or at most equal to 0. It is non-negative, therefore. It is unbounded above, And usually, well, always it has a minimum that depends on the vector t and x. So our goal is to find the thresholds and the quantization points that minimize the distortion function. This is done by using the iterative algorithm that we mentioned before. The necessary condition for the existence of a minimum is that the partial derivatives are all equal to 0, so that we calculate the partial derivatives with respect to the thresholds and then with respect to the quantization points. We start with the thresholds. We take the derivative of d with respect to ti. That's the derivative of d. This is the derivative with respect to ti of a sum of integrals from tj minus 1 to tj of x minus xj squared times the probability density function. Now, since we are looking for the derivative, the partial derivative with respect to ti, we need to look when ti is present in one of these integrals. Notice that ti can only be present in correspondence of a lower limit or an upper limit. Now let's recall one thing. If we take the derivative with respect to x of the integral from a to x of a certain function f of u du, what is this derivative? This derivative is f of x, if this is an upper limit. If x appears in the lower limit, it is if we have the derivative with respect to x of the integral from x to b of the function f, it's minus f of x. Now, let's see when ti appears in one of these two positions. Well, when j is equal to I, ti appears as the upper limit. Only the upper limit, because the lower limit will be ti minus 1. And therefore, this contributes with the function that we want to integrate calculated in correspondence of ti. And this gives ti minus xi squared multiplied by fx of ti for j equal to I. For j equal to I plus 1, it appears as a lower limit. And in that case, it contributes to the derivative with minus ti minus xi plus 1 squared times probability density function ti. That is exactly the product of these two terms. This difference must be equal to 0, okay? Now, we can assume in general that fx of ti, the probability density function of ti, is different from 0. And therefore, the equation that we have to consider is that this quantity must be equal to 0, the factor of the probability density function. If we do a simple simplification of this difference of square, we can see that it is equal to 2ti minus xi plus 1, which is the sum of these two terms multiplied by the difference that gives xi minus xi plus 1. Xi minus xi plus 1 cannot be equal to 0 because we assume that the quantization points are different. It would be useless to have two equal quantization points, and therefore we get these equations. Ti is equal to xi plus 1 divided by 2. Therefore, the thresholds are equidistant from the two adjacent quantization points. And this is important because it is something that we are going to see again when we are going to talk about the multidimensional extension of this result. In the one-dimensional extension, we can see that the thresholds are equidistant from the adjacent quantization points, and therefore they are in the middle of the segment that joins two quantization points. So we have an equation for the thresholds that requires the knowledge of the quantization points, but we don't know the quantization points. Continuing our calculation of the partial derivatives, we calculate the derivatives with respect to the quantization points. And these derivatives are involve only one of the n integrals that we have in this sum. The integral that corresponds to j equal to I, because that's the only case where xi appears in the integral. And that's the integral of from ti minus 1 to ti of x minus xi squared times the probability density function. The derivative is the integral from ti minus 1 to ti of 2 times xi minus x times the probability density function, which, and this is set equal to 0. This equation can be solved, and it gives that xi is the integral from ti minus 1 to ti of x times the probability density function divided by the integral over the same range of the probability density function. This is called the conditional expectation of x with respect to the conditioning clause that x is in the ith quantization interval. Conditional expectation of x given that x is in the ith quantization interval. That is ti minus 1 ti. This is also called the centroid of this quantization interval. The centroid with a uniform distribution would be the middle point. If the distribution is not uniform, is a point inside the interval that in physics would represent the gravity center of the interval with respect to a mass distribution given by the probability density function. We call this the centroid of this interval given the probability density function. So we have two sets of equation. We have n-1 equations that give us the thresholds if we know the quantization points, and another set of n equations that give us the quantization points if we know the thresholds. And for this reason, we can implement an iterative algorithm, because we start with the thresholds, then we get the quantization points, and then we obtain again the thresholds and the quantization points and so on. And this is just the description of the iterative algorithm, the Lloyd algorithm. We initialize the quantization points, the quantized values, and we call them x with this superscript 0. That means that this is the initialization step, and we set them equal to some x0. That's usually a random choice so we pick up a certain set of real numbers at random, and we just need to sort them in an increasing order, because the quantization points are sorted. They go from the minimum to a maximum. And we use these random values to initialize the vector of quantization points. In some cases, we can exploit the symmetry of the probability distribution. So if the probability distribution, like in the case of the Gaussian distribution, is an even function, well, of course, there is a symmetry with respect to 0. And in that case, we can assume that the quantization points are positive and negative values, with some caution, because if n is even, if the PDF is symmetric, and if n is even, we take some random positive values, and the corresponding negative values. If n is even, because in that case we have, for example, 2 positive and 2 negative, if n is 4. If n is odd, it's a little bit different, because we have to add the zero. The zero is always present. So if n is odd, we also add 0. Zero is always present as a quantization point when the number of quantization points is odd and the probability density function is symmetric. Actually, this is not strictly required. We can also choose the points completely at random. But if we do this, the algorithm is faster. It converges faster. Because it's like we use our knowledge, the property of the probability density function to push the algorithm convergence to converge a little bit faster. So after the first initialization step, we have an iterative sequence of steps that corresponds to the calculation of the thresholds and of the quantization points, iterated quantization points. So in the first case, we set Ti n plus 1 equal to xi n plus xi plus 1 n divided by 2. And we obtain n minus 1 thresholds. These are the inner thresholds. Let's remember always that we always have the true extremal threshold T0 equal to minus infinity and Tn equal to plus infinity. Oh, well, actually, this is not completely true because the probability density function can be defined over a finite range. If it is defined over a finite range, if the PDF is defined over a finite range AB, then T0 is A and Tn is B. They are the extreme points of the probability distribution. In this way, we calculate the next iteration threshold. So this Ti n plus 1. By using this vector of the next iteration thresholds, we can calculate the centroids by using this expression. And in this way, we obtain the quantization points for the next iteration. Once we have these quantization points, we repeat the calculation of the thresholds for the next iteration, and then the calculation of the next quantization points. And we repeat this like this for n that goes from 0 to infinity. At a certain point, we have to stop because as all iterative algorithms, at a certain point, they stop. And we do this, we stop by considering, for example, the difference between the quantization points at iteration n plus 1 and the quantization points at iteration n, and we can calculate the squared Euclidean distance between these two vectors. And when this becomes sufficiently small, that is, it falls below a convergence thresholds, then we stop the iteration. We break the loop. Now we are going to see an example of application. Actually, it's a simple example, but it has the advantage that it's possible to do the calculations analytically and extends the previous example that we have seen before. We still consider the Gaussian with zero mean and variance 1, but this time we use 4 quantization points. Therefore, n is equal to 4 this time. R, the number of bits per symbol, is equal to 2. And in fact, it's the logarithm in base 2 of 4. We also can say that we have a 4-level quantization because there are 4 quantization points. We quantize our random variable over 4 levels. Now, we can exploit the symmetry of this probability density function. We have already considered that before in the previous example. In the previous example, we had only one threshold. If you remember, the threshold was 0. And the 2 quantization points were minus a and plus a. Okay. In this case, we need more thresholds. Actually, we need 3 thresholds. And we, because of the symmetry, we put them in minus t, in 0, and in t. And the quantized values, we call them x1 and x2 over the positive part of the real axis, and minus x2 and minus x1 over the negative part. So that in total, we have minus x2, minus x1, x1, and x2. And of course, x1 is lower than x2. These are the iterative equations. Tn plus 1 equal to x1 n plus x2n over 2. That's the midpoint equations. And I'm skipping the detailed computation of the centroids. They are given by these 2 expressions here. x1 n plus 1 and x2 n plus 1 are given by these 2 expressions. As you can see, they involve a special function, that is the Q function. The Q function of x is just the probability that a zero mean unit variance Gaussian random variable is greater than x, and therefore it is 1 over the square root of 2 pi times the integral from x to infinity of the probability density function e to the minus u squared over 2 du. That's the counter-cumulative probability distribution of the normalized zero mean unit variance Gaussian random variable. Maybe you have already seen a related function, that is the complementary error function. There is a relationship between these 2 functions. Q of x is equal to 1/2 the complementary error function of x over the square root of 2. In some books, they use the complementary error function, the RFC. In other books, they use the Q function. I personally prefer the Q function because it is more directly linked to the probability distribution. The error function, well, it's something different. By some additional effort, we can calculate an expression for the distortion D that depends on X1, on X2, and on the threshold T. That's a little bit complicated, but I know, but it can be calculated directly from the definition. And this is how the Lloyd algorithm works for this example. We start with a specific configuration of X1, X2, and the threshold T at iteration 0, which I chose somewhat arbitrarily, equal to 1, 1.5, and 2, just to remember how we have located our quantization points. If 0 and T are located in this part of the positive real axis, here we are going to have X1, and here we are going to have X2. And let's recall that T is the midpoint of the segment joining X1 and X2. And this condition is satisfied by the initialization, which is not necessary, but well, it's always good to have it already this way. Next, for the following steps, we calculate the iterative refinements of X1, X2, and T. So first of all, we can calculate the next T, that is 1 plus 2 divided by 2, and in fact, this is 1.5. And next, we calculate the two centroids. They are 0.62 and 1.94, more or less, and the corresponding distortion. Next, we pick these two centroids and calculate the average. We obtain 1.28, the next threshold. And then we calculate the two centroids. And the distortion passes from 0.16 to 0.13. And we go on like this until the distortion converges. You can see that the distortion converges at the 8th iteration with the 4 significant digits. However, the distortion converges, but the quantization points and the threshold are still different from one iteration to the next. And so we need to have more iteration to have a convergence also of the quantization points and the threshold. Actually, it requires around 20 iterations for convergence to 4 digits. Okay, that's the way the Lloyd algorithm works and allows us to implement one-dimensional quantization. our next step is extending this algorithm to multiple dimensions. And we're going to do this after the break. Okay, now we are going to extend the previous analysis. Can you hear me well in the back? Can you hear me? Okay, thank you. We extend the previous analysis from the one-dimensional case to the multidimensional case. This we are going to consider what is called vector quantization, because it involves the quantization of random vectors instead of scalar random variables. Vector quantization is mainly realized by resorting to this algorithm, the Linde-Bouzeray algorithm. This is a relatively old algorithm. It dates back to 1980, and its creators are these three guys, Linde, Bouzeray, and Gray. And similarly to the Lloyd algorithm that we discussed in the previous part, the LBG algorithm is iterative, and this time it's an iterative with vector quantization algorithm instead of the other one that was an iterative scalar quantization algorithm. Again, the goal of this algorithm is minimizing the average quadratic distortion, but in a multidimensional domain. This algorithm, I see there is a question in the chat. Let me see. When is the deadline of the assignment 2? You find all the deadlines, Mr. Kamyar, in an extensive note that I have uploaded over the website. So please read the note. Thank you. I was saying, this iterative algorithm converges to a locally optimum solution that is not a global optimum. And because of this, we need several random initialization to find the global optimum. This is worth giving some additional explanation. What is the meaning that you have a global optimum or a local optimum? When if we are looking for a minimum, this is a function where it is easy to understand that we have a single global minimum. And the meaning, the reason why this is a single local minimum is that this is a convex function. When a function is convex, it has a single global minimum. When a function is concave, that is the convexity turned upside down, then there is a single global maximum. We cannot say anything about the maxima for a convex function, of course. But for the minimum, we can say that there is a single global minimum. What happens if the function is not convex? Well, you may have a function that looks like this. For example. And you can see that you have two minimum points. This point here and this point here. This is the global minimum, assuming that we consider only the range of the paper, and this is a local minimum. How do we reach the local minimum or the global minimum? Let's say that we are a little ball and this is a surface. If we put our little ball over this surface in this position, then the little ball rolls down to the global minimum, okay? But if we put that in this position, the little ball rolls down to the local. But we don't know in advance where we should put our little ball in order to reach the global minimum, okay? And by the way, this approach essentially is mathematically implemented by the gradient algorithm. The gradient algorithm essentially does what we would do with our little ball. It rolls down to the minimum or it rolls down to a local minimum, depending where we start. So the only thing that we can do, if we cannot reshape the problem in a way that it becomes convex, we can make mini trials and we can put our little balls in several random initial positions and consider all the convergence points of our little ball. So if we put it, for example, the first time we put it here, we are lucky. But if the first time we put it here, maybe the second time we put it here, then we need a third trial, a third attempt to find the global minimum. So we take several initial random positions and hope for the best. This is global maximization, global optimization, essentially. Several repeated trials with different initial positions, and every time we take a note of the minimum that we have reached, and we say that the global minimum is the minimum of these different minimum points. There is no guarantee that we reach the global minimum when the function is very complex, because it may happen that we have some function looking like this. So if we have a function like this, we can put our little ball here and we reach a local minimum. We can put it here. We have to make many trials, many initializations until we reach something that looks like a good minimum point. But there is no guarantee in that case. Unfortunately, there are some optimization problems that are difficult to solve because of this initialization problem. However, since there is not very much that we can do, there are some sort of educated global optimization algorithm. I don't know if you have heard of Adam. Adam is not the husband of Eve, but is an algorithm that is used for deep learning to find the inner parameters. And essentially, in deep learning, we have global optimization problems that are non-convex, global minimization problems that are non-convex and require many optimization. Essentially, the big idea here is that when you reach a local minimum, then you try to move away from the initialization point sufficiently until you get another local minimum that is sufficiently better than the first one. And but it's not, I mean, it's not foolproof. It doesn't work 100% of the times. It gives you a good minimum, but there is no guarantee that you reach the optimum, especially when the parametric neural network has a large number of parameters. Anyway, usually it is enough to reach a good local minimum, even though it is not a global minimum. This digression is just to say that the LBG algorithm does not converge to a global minimum because the problem is not convex, and so we need repeated initializations in order to reach a good minimum that is not necessarily the global minimum. The LBG algorithm has many applications in several areas of machine learning, and machine learning, artificial intelligence, these are all names in the same family that have included the concepts that were previously living autonomously in other areas, but they have been eaten by machine learning and artificial intelligence. So that data compression now is considered to be a part of artificial intelligence. And LBG is used in data compression, is used in feature representation, like the k-means clustering algorithm, in pattern recognition, prototype-based learning, anomaly detection, generative modeling, and I stop here because the list goes on quite long. Just to tell you that it's not an algorithm that has no significance. It's quite significant in the context of modern technology, modern applications, modern technological applications. But let's go to the substance of the algorithm. Again, we consider the distortion, the quadratic distortion function, that this time is written in a slightly different way to emphasize the fact that we have a function that we call the quantization function. This function applies to the vector x and produces for the vector x, it produces a number of possible quantization points. In other words, your random vector x belongs to a certain region, R. The quantization function, Q, maps R into a set, and this set is represented by n quantization points. R is included in a multidimensional space. Let's say that it's R to the M, and also the hexabi, the vectors hexabi, belong to the same R to the M, and they also belong to the region R, because we assume that the quantization points are inside the region where our vector lives, where our vector is defined. Because of the definition of the distortion function that depends on the distance of the vector x from its quantized version, from its corresponding quantized points, the quantization vector, assuming that the quantization vectors are these ones, x1 hat, x2 hat, up to xn hat, the distortion is minimum when the random vector x is quantized to the closest of these n quantization vectors, that is the closest x at I. And this is formally written by saying that q opt of x, the optimum quantization function applied on the vector x, is the argument of the minimum of the square distance of x to x hat, the difference of x minus x hat in squared Euclidean norm, where x hat is one of the possible quantization points. Maybe this is redundant, but it's worth telling it just in case somebody doesn't remember immediately. If we have a function like this, let's say that this is f of x, then the minimum is in the point x0, and this point here, the minimum point, has coordinates x0, f of x0. Okay. Now, f of x0 is the minimum over x of f of x. Okay. Let's say that x is the horizontal axis, but this can be done also in a multidimensional setting. For example, if x is a two-dimensional vector, we can have a three-dimensional vector representation, a three-dimensional representation of a function of two variables, and the minimum is a point in a two-dimensional plane. Besides the minimum, we also have to give a name to the point that achieves the minimum. And that's the argument of the minimum. So x0 is called the argument of the minimum over x of f of x. In other words, the argument of the minimum is the point where the minimum is achieved. And therefore, in this previous application of the argument of the minimum is the value x hat in the set, in the discrete finite set, x hat 1, x hat 2, up to x hat n, that minimizes this thing. So given x, we are looking for the x hat that minimizes this thing. So if, for example, we have that this is x at 1, this is x at 2, and this is x at 3, and my point X is located here, which is the argument of the minimum of X minus X at squared Euclidean norm, is X3, X at 3. So in this case, we have that Q of X, where X is this point here, that gives X at 3, the closest point among the set of available points that are the quantization points. Now, the proof that this quantization function defined in this way is actually optimum, that is, that it minimizes the distortion, the average squared, the quadratic distortion, the average squared difference, can be obtained by noticing that by the definition of the Q-opt function, the square distance between X and Q-opt of X, which is the closest quantization point to X, is lower than or equal to the square distance from X to a quantization point that may be different from the optimum one, because it may be another one, and it's obtained by applying a different quantization function. So we have this property, this optimality property, without the expectation. But this holds for every X. This property, this inequality, is valid for every X. Therefore, we can apply the expectation, and also the expectation that corresponds to the distortion, to the minimum distortion, will be lower than the distortion corresponding to any other quantization function. This property allows us to say that the optimum quantization function partitions the domain of our vector X, the domain R, into a set of Voronoi regions. Probably you have already heard this in other contexts. The Voronoi regions are essentially the regions that contain the points that are closer to a certain set of fixed points, that in our case are the quantization points. So the Voronoi region R sub I is the set of X's such that Q-opt of X is X at sub I. And therefore the Voronoi region R sub I is the set of points that are closer to X at sub I than to any other X at sub J. So for example, if we have to consider a two-dimensional representation containing these 4 points, 4 quantization points, the 4 corresponding Voronoi regions can be obtained in this way. You should note one thing, that the borders of the Voronoi regions are in this two-dimensional plane, are the lines that separate the pairs of quantization points at equal distance, that they are the axis of the segments joining the quantization points. So if we want to draw manually the Voronoi regions, we can just obtain geometrically the axis of the segments joining, for example, x1 with x2, x3, and x4, and we obtain these three lines. And these three lines, the limit, the Voronoi region, are 1. In the case of x4 hat, we only have two lines, because the line that corresponds to the segment that joins x4 hat with x2 hat is farther away from the two lines that are the axis of the segments joining x4 and x1 and x4 and x3, so that it is irrelevant. And in this way, we can obtain manually the Voronoi regions by using a construction based on the axis in a two-dimensional plane. If we were to obtain the Voronoi region in 3 dimensions, instead of considering the axis, we should consider the planes that are equidistant from adjacent quantization points. It would be a little bit more difficult because the 3-dimensional representation is always more difficult to visualize, but it could be done. Of course, if we increase the number of dimensions, only an analytic representation is possible, because we are unable to represent things in more than 3 dimensions. Now, this property that the optimum quantization function corresponds to the choice of the closest quantization point is called the partitioning step of the LBG algorithm. The partitioning step is one of the 2 iterative steps that must be implemented by our iterative algorithm. In the one-dimensional case, the quantization, you can see that we obtain from the quantization point the Voronoi regions. What are the Voronoi regions in the one-dimensional case? They are the intervals that correspond to each, the quantization interval that correspond to the quantization points. And because of this property, if we have 2 adjacent quantization points in the one-dimensional domain, the quantization function maps everything up to this threshold that we called T1 with the previous numbering. Everything that is below T1 is mapped to x at 1. Everything that is after T1 is mapped to x at 2 until the threshold T2. So that the Voronoi region in the one-dimensional space is R1, R2, and so on. And instead of being delimited by lines, like in this example in 2 dimensions, the Voronoi regions in 1 dimension are delimited by points. In general, in n dimensions, in m dimensions, the Voronoi region is delimited by a hyperplane with m-1 dimension. And when m is equal to 1, the hyperplane with 0 dimensions is the point. So you can see that this is just a direct extension of the previous algorithm. The partitioning step, therefore consists of obtaining the Voronoi regions, and the other step is the centroid step that is very similar to the calculation of the centroids in the Lloyd algorithm. In this case, in the centroid step, we assume that the quantization function is given, and therefore the Voronoi regions are also given, because it is equivalent to have the quantization function or the Voronoi regions. Inside the Voronoi region, we find the quantization point. Initially, we start from the quantization point and we define the Voronoi region. But in order to minimize the distortion, we can move the quantization point inside the Voronoi region in order to improve the distortion. This corresponds to minimizing the function d with respect to the quantization point. So keep in mind that we have fixed the Voronoi region. Then, since d is the expectation of the square distance between x and q of x, this can also be written as the sum over I of the probability that x is in the ith Voronoi region multiplied by the expectation of the square distance of x from its quantization point, given that x belongs to the Voronoi region. This is just the application of the definition of conditional expectation. The conditional expectation is simply the expectation of a random variable under a certain conditioning clause, and averaging the conditional expectations gives us the unconditional global expectation. However, when x belongs to the ith Voronoi region, what is q of x? It's always equal to x at sub I. So we can replace this with x at sub I. And then we arrive at this expression. The sum of the probabilities that x belongs to the ith Voronoi region times the conditional expectation of the square distance between x and x at sub I, conditioned to the fact that x belongs to the ith Voronoi region. And we have n terms like this, and we add them together to obtain the overall distortion. Now, if we want to minimize this function with respect to the x hat sub I, we can notice that each of these n terms depends individually on each of the x hat sub I. The first term depends on x hat 1 and nothing else, because R1 doesn't depend in principle under our assumption, because it's fixed. It doesn't depend on the other x hat I. And similarly, x hat 2, the second term depends only on x hat 2 and so on. So we have a sum of functions that depends individually on the different variables. If we want to minimize the sum, we can just minimize each function. And this is what we do. We minimize this term with respect to x hat I for every I from 1 to n. Of course, this probability can be ignored because it is just a constant positive term. We have just to minimize this with respect to x hat sub I. And to do it, we consider the variation of this expression with respect to x hat sub I. I don't know if you have already encountered the concept of variation. Essentially, the concept of variation is just the same thing as the differential. If you have a function for a function f of x, the variation is delta f of x defined as f of x plus delta x minus f of x, where delta x is an infinitesimal displacement of x. In other words, we move a little bit x away from its original position, and we get a displacement that is called the variation of the function f of x. If we are looking for a minimum and also for a maximum, but in our case, we know that we are going to find a minimum, the variation must be equal to 0. So with a minimum, the variation is equal to 0. But this is not all. It's equal to 0 for every delta x. Why this is important? This is important because in the common one-dimensional setup, delta x is just a number. In this case, it is a vector of infinitesimal numbers. And for this reason, we have to consider the arbitrarity of the direction of this infinitesimal vector. And that is what we are doing here. So first of all, we calculate the variation of the squared Euclidean distance from x and to x at I with respect to x. Now, x minus x at I squared Euclidean norm is also equal to the inner product of x minus x at I by itself. Calculating the variation follows exactly the same rules as calculating a differential. So the variation of this is equal to x minus x at I scalar product with the variation of x minus x at I, which is just delta x, because x at I is fixed. And this is one of the two terms that we have to consider when calculating the differential. The other term is obtained by multiplying the variation of the first term scalarly with x minus x at I. Obviously, these two scalar products are equal to each other, and therefore this is just 2 times x minus x at I scalar product, the variation delta x. In this way, we arrive by deriving, by taking the variation under the derivative to the expectation of 2 times x minus x at I scalar delta x. This expectation is conditioned on the fact that x belongs to the region R sub I, and this is equal to 0 for every delta x. We can remove the 2 factor and consider that delta x is arbitrary, can be arbitrarily distributed, and so the only way that we can satisfy this equation is by having that the expectation of x minus x at I conditioned on the clause that x belongs to the ith Voronoi region R sub I is equal to 0. But then, and finally, we can expand the expectation, and the expectation of x at I, which is a constant vector, condition with respect to this clause, but this is irrelevant with respect to x at I, which is a constant, gives x at I. And x at I must be therefore equal to the expectation of x conditioned on the fact that x belongs to R sub I. And these are the vectors that are called the centroids of the Voronoi regions R sub I. In this way, we have obtained two different sets of equations. The second set is for I that goes from 1 to n, and we label this with a diamond. The other one, this one, was labeled with a star. We can use the equations obtained in the partitioning step and in the centroid step to obtain the iterative LBG algorithm, because the two equations star and diamond must be satisfied simultaneously, and this can be done approximately by using an iterative algorithm. The iterative algorithm is divided into two main steps. The initialization step, consisting of choosing n initial random quantization points, x at I0, and defining the corresponding Voronoi regions, Ri0, and then iterate for n, that is the iteration index that goes from 1 to infinity. These substeps, the substep A, that is the centroid step, consists in calculating the centroids by using the centroid equation, that is this equation here, that is based on the Voronoi regions that we have at the previous step. You see that we have n-1 here, and therefore we calculate the centroids of the previous Voronoi regions, and this is the centroid step. After this step, we update the Voronoi regions, and this is the partition step or partitioning step. During this step, we recalculate the Voronoi regions in order to minimize the distance between the new quantization points and the vector x, and at the same time we calculate the distortion function for these updated Voronoi regions. We use the distortion function to decide when we can exit the loop. This is one possibility. The other possibility is compare the quantization vector xi at the quantization vectors xi at, and for example consider the sum of xi hat n minus xi hat n minus 1 with the squared Euclidean norm. If at a certain point this goes to 0, because there is convergence, and this and then at this point we stop the iterations. So there are at least two different stopping criteria. The first one is based on the distortion. The second one is based on the positions of the quantization points with respect to the previous iteration. When instead of considering the sum, we can consider the maximum distance, or there are different possible metrics. This one is quite simple. Also, this one is okay. Probably since our goal is to minimize the distortion, probably this one is even better. If instead our goal is to find the location of the quantization points, the optimum location of the quantization points, and therefore the optimum Voronoi region, then this one should be chosen. But it's somewhat arbitrary. It depends on the application. Anyway, each of them can be a stopping criteria. We have seen in the previous example that convergence of the distortion tends to happen more quickly than the convergence of the quantization points. Let's recall, however, that the convergence is to a local minimum. And if we want to obtain convergence to the global minimum, if we want to approach the global minimum, we need to use several initializations, that is, several random quantization points x at I 0, and collect the distortion, the optimum distortion, or also the optimum quantization points corresponding to the minimum distortion, because in this way we can have a global optimization algorithm, as I mentioned before. Okay, that's all for today. Tomorrow tomorrow I'm not going to see you. Next week I'm going to continue with the information theoretical approach, and the last 3 classes will be dedicated to the second part of the assignment. Okay, bye-bye.